Hi everybody, this is Justin Gibbs. I've had a few folks asking about the radar process that we follow in the National Weather Service and in general what we teach at WDTD when we're interrogating and warning on severe storms. And this is just sort of my take on it. This isn't anything that you want to lock all the way in on, but maybe some things that will be helpful to non-meteorologists and also maybe some meteorologists. So I'm going to talk briefly about some of the newer things that we've been doing towards our approach with severe storms. Now, if you end up in the Weather Service, now first you have had to have gone and gotten a 4-year degree in meteorology where you learn about severe storm processes and then all the physics and science on the big scale, the small scale, and everything. You've got to be fully trained. And then we put you through our courses at WDTD. And here's a look at one of them. This is the Radar and Applications course. And it's 120 hours. And each of these are about 15-minute modules that talk about the way the radar works, the characteristics, sampling issues, things that you'll need to know when you're interrogating radar data and making warning decisions, Doppler velocity patterns, the algorithms that are produced by the 88D, rainfall products and estimations, and then we talk about supercells and multicells and all the different types of cells and dangerous things to be watching out for. We have a topic on flash flooding, storm-based warnings, and then you come to Norman for a week and we put you through 40 hours of simulations and evolutions and exercises. And then when you get done with that, you take the warning operations course, severe weather track, and then we've also got a human factors track that teaches you about human decision making and how to optimize that in a team. We've got tornado warning guidance where we go even further into the way that we approach and attack this. So there is, and then there's the flash flood track, and there is multiple, let's see what else, wind or weather track. The bottom line, there's a lot of training that goes into what a weather service meteorologist is typically going to get before they begin to make warning decisions. And then there's also in-house training, and there's at that point you get to the point where you can read your own journal articles and write your own journal articles in a lot of different places. So a lot of training goes into this. So this is not meant to be exhaustive or anything like that. This is just a big picture overview, kind of how we approach and attack it. And I thought it might be fun to do this afternoon. So when you're looking at a radar from the top down, you're typically, if you're using radar scope or you're looking at TV, you're typically going to maybe be seeing something like this on your screen, which is radar reflectivity. And then maybe you'll see velocity, looks like that, and then maybe you'll get correlation coefficient. A lot of television stations call that the debris tracker, because we can use it to identify tornado debris when other conditions are met. And then there's storm relative velocity, which that calculates the storm motion and factors that out so it's easier to see rotation in the storm, where the base velocity is just relative to the radar. And the way that we collect that data, you only typically will see the lowest 4 tilts, but it is in a volume coverage pattern. And so the radar sends out a beam of energy down low and goes very slightly higher, usually 0.4 degrees angle higher. And it goes a little bit higher, all the way up until we have sampled up to about 20,000 feet. And then we start to space things out a little bit more and get up to eventually to 19.5 degrees above vertical, which is where the top scan goes. And then it takes a certain period of time to make those collections. You can see here's a map of the how long each cut takes. 31 seconds for a lowest elevation sweep, and that is because it collects the reflectivity data, which is the reds and greens that you would show rain and hail and things, and then the velocity data in a separate cut, where these other cuts, as they get higher, do it all in one, so it only takes 13 seconds. We've had something called sails, where instead of just going the way we used to do it, which is going up to this VCP, and you just keep going all the way to the top, it will stop about here and then go back and scan the bottom again, go back up here and scan the bottom again, and it can do that up to 3 times every time we do a volume scan. and each full volume scan takes about 7 minutes. Now you'll hear sometimes people say, well, the XRAD data is not live, it's delayed by 7 minutes. Well, that's not really true. It takes 7 minutes to do an entire scan, but we're getting the data back pretty much instantaneously. It's collected by the radar, the power hits the antenna, it's processed for about a few seconds. But by the time the full volume sweep is completed, we get it within a few seconds. So we're seeing virtually live data. Now, what can happen with a volume coverage slice is that you can be looking at data that is from a slice that was collected earlier, where we've gone up through the volume scan, and your current data is maybe 4 or 5 minutes old because the radar is up here scanning and collecting data up here, and it's not collecting anything down low. So you might be looking at older data, and it appears delayed if you're just looking at 0.5, because we're only, which is the lowest, or the lowest available beam angle, because it appears it's only collected every 3 or 4 minutes, and maybe even up as much as every 5 or 6 minutes, depending on what VCP you run in. And to severe weather mode, typically the Weather Service will run in VCP 212 because it has good, it seems to have all the best things we want as far as the complete. You can see some of these other VCPs have bigger gaps in them, so they run a little slower. There's advantages and disadvantages, but for the most part, VCP 212 has the combination of good quality data and speed that we want, and full and volumetric coverage to give us our best chance to see what we want to see in the amount of time that we want to see it. I'll go to this slice here. Typically, when I'm approaching, we have all kinds of different ways we can visualize the data. When I'm not on an AWIPS, I'll typically view it in this GR2 software, and it will allow me to go up and down through the tilts very quickly as the data comes in. And then I can end up here. You can see we're looking at 25,000 feet roughly above the radar level, and all the way up to the top here at 40,000 feet. And it'll go even higher. But we also have a process called AVSET, which is, if you'll notice earlier, we had 13 or 14 slices to cut through, and we only collected 11. The radar can detect once it gets to this level, there are no returns, no reflectivity, so there's no reason to go any higher. So it will then restart the volume scanning. It'll go back down to the ground and start over, which is a feature that we added a few years ago. It's been about maybe about 10 years now, and it's really nice. It's super handy. We really like it. The sales is also relatively new. The ability to go back down to the ground is something that we've only done the last few years. So anytime that I'm looking at a storm, we're looking at the full volume scan of this storm to give us a 3D picture of what's happening. In this case, we've got this is early in the life cycle of what became sort of the quad state supercell on December 10th, 2021. And we're looking for different characteristics to identify what the probability is that we're going to have tornadoes or severe weather. Reflectivity, typically I'll run up here in the top left, top right. I usually run base velocity, which is ground relative. Top left, I'll run storm relative velocity, and then the bottom right, I'll run correlation coefficient. And I'll switch this panel out with ZDR, which is differential reflectivity, and KDP fairly frequently as well. And now there's a 9 panel that I'll run on AWIPS that actually has it where I can see it all at once. And that's typically what we send our RAC graduates home with, is the ability to see it all in one deal, just on GR2. That's just what you have, and you can use that to help you make decisions as well. And I don't, use, there's other dual pole elements in GR2 that we don't really use all that much, like raw KD or raw phi and things like that, but it doesn't really come up to be super useful most of the time. And we'll get this new data every 15 to 30 seconds where it goes in and collects it. In this case, we've got a storm that was in a very favorable tornado environment. Your significant tornado parameter was about 4 or 5, maybe even a little higher than that at this point. And this is just sort of a messy, sheared convective cell, a little bit of a meso here, and then it gets a little bit more organized in the next volume scan. And typically when I'll see something like this, I'll start measuring the rotational velocity of those mesos. In this case, it's 41 knots at 2 nautical miles, which is, yeah, interesting. It's not super strong. It's at 6,000 feet. It's on tilt 1.4, but it's very common in supercells that you'll begin to get a meso forming aloft that gets a little stronger, and then eventually it gets a little tighter before you start to see much going on down here at the lowest elevation angle. Down here, we've got, and this is in a pretty decent area of power return. It's something else you got to look out for with your velocity, is making sure that your reflectivity is also relatively high. And here it's much broader. You got 34 knots at 3 nautical miles. And we have a tool in AWIPS that we can use too to help us measure those diameters quickly. And you can see down here at 0.5, now it gets a little spark hike, a little bit more froggy looking, a little stronger and much stronger there. But aloft, we were already starting to get those enhanced velocities here, 4 or 5 minutes before. This is 43 knots at 2 nautical miles. And then here it tightens up even more. You've got 40 knots at 2.2 nautical miles. It gets a little bit larger and broader. And then the depth of that meso also increases, and that's one of the things we like to look at. So here you've got a meso forming. It's at 3,000, 4,000 feet above radar level. But it's also continuing now to, maybe even right here, but for certainly right here. That's 9,800 feet. So you got 4,000 foot base, 10,000 foot top. You got about a 6,000 foot, maybe even 8 to 10,000 foot deep meso here. And when you get mesos in supercells above 8 to 10,000 feet, you tend to get higher potential that that storm is going to produce a more significant tornado. And you've also got to be constantly fighting data quality issues. You see down here, that data, you've got these blue inbounds. They're in an area where the inflow should be sweeping outbound. So we're looking from the Little Rock radar, so those reds should be going away from the radar. And what's happening here is velocity de-aliasing, where all of this is actually giving, if you turn the velocity de-aliasing off, it's giving inbound returns at 19 knots. And what's happened here is we've exceeded the velocity maximum that we can detect without having velocity aliasing come into play. In this case, it looks like, and you can tell where your maximum, what we call the Vmax is, by going to the point that you then flip around into de-aliased or aliased velocities, which is right here. It's about 45 knots, and that's pretty low. But that is because in this case, the PRF is set to have a Rmax, or maximum range from the radar, of 78 nautical miles before you get into range folding. So you've got, it's a trade-off that we make. The further away from the radar that we can see without range folding coming into play, the lower the velocity values before we get velocity de-aliasing. We get velocity aliasing rather, and de-aliasing is the algorithm that is run that mathematically corrects those values. And in this case, that de-aliasing algorithm appears to have failed and has incorrectly unfolded them as inbound velocities when they should be outbound. But honestly, meteorologists get so used to seeing that we don't even see it, we don't even realize it's there until we take a second look. Where in here, this becomes a little more of an issue because you have relatively strong velocities that are in the right place, and there's still that pause of, is that correct? Because that's a 68 knot inbound. That'd be pretty strong next to 44 knot outbounds. That would be a rotational velocity of 56 knots at less than 1 nautical mile, where if I go out here to where these velocities look a little better, it's more like 41 knots at 1.2 miles, which is also pretty good, and kind of getting into the, especially with it being down low, that's a pretty strong low level circulation, kind of getting into tornado warning territory. And by this point, a tornado warning actually had already been out on this storm for a couple minutes. They'd already seen the increase in the mid-level meso here and popped it before that low-level circulation tightened up down low. So that's one of the things we run into is, I imagine all this data is aliased, and then where does that de-aliasing stop? And where is it correct? Is this actually outbounds that are folded over, or is it inbounds? And this came up a lot in this December 10th storm, and it really rekindled my interest in looking into velocity de-aliasing. And we have a more robust algorithm in AWIPS that typically catches things a little bit better. But there are still lots of differences in how the velocity de-aliasing algorithms handled each storm. And I'm going to load later velocity on this storm, because this one gets pretty interesting. As most of you know, but as we're doing, anytime I'm looking at supercells, I'm looking at that meso aloft, even when I have a tornado down, because the meso aloft will still give you clues as to how the rest of the storm, what the future of that storm holds. If you begin to get a meso well to the northeast, or well to the east rather, oftentimes that precedes an occlusion. It'll precede, you get a new meso taken over to the east, maybe you're going to get an occlusion in the next 10 or 12 minutes. If the meso weakens dramatically aloft, oftentimes it'll preclude a weakening at the surface. It may take 10 or 15 minutes. And then if you get a big intensification aloft, oftentimes then you're going to get an intensification of the tornado on the ground. And then we will then compare the lowest available reflectivity velocity, or the velocity values that give us sort of our current intensity estimate of the tornado. So we're using the tilts aloft to predict the future, and we're using the ground, the closest to the ground slice, to assess what's happening right now. And that's where our considerable and catastrophic tag decisions are made, using the lowest data. And we just do that over and over again, sometimes for 2 or 3 hours, 5 or 6, 7, 8 hours at a time. So here's a little bit later in this storm, and low-level circulation is more obvious. Low-level rotational velocity is around 46 knots. And it's real tricky with this rotational velocity, because you can measure way out here, get 80 knots there as a max, and you got a VROT of 57 at 2.24, which maybe that is more appropriate given the situation. But you could also factor in 52.9, and sometimes I'll take kind of an ensemble. Now the good thing about rotational velocity is, even if I take this one, it's at 50 knots, and that's still getting into EF2 range potentially. So a lot of this becomes academic when you start getting those bigger values, and you don't have to spend as much time fussing over, is it 56, is it 59, because it doesn't qualitatively make any difference in terms of impact. It's still significant. So as this little storm sauntered across northeastern Arkansas, I was watching that night for a big increase in the meso beyond even what we were seeing here. Here I'd be measuring 44 knots, 1.77 miles. That's still a little bit weak and a little bit broad for like the biggest of tornadoes, but it's the depth of the meso was what struck me this night, and what sort of made it clear this was going to be a serious problem, because the low-level meso here, I'm getting it at 4,000 feet. It presumably goes pretty close to the ground. And then it tops out maybe here, and that's still 10,000 feet deep, and you're getting some velocity de-aliasing algorithm errors there, and it becomes a little more difficult to tell. But then right in here, you start seeing, even down low, you start seeing those much stronger velocity values start to pop up. You get some 52 knots at 2 nautical miles, still a little bit broad. And then you start to see the enhanced velocities show up down low. This storm is a little bit weird in that the enhanced velocities really took off simultaneously, kind of at all levels. A lot of times you'll get the mid-level meso, 10, 12,000 feet in here, you'll start to see a spike. This storm was weird in that it's the whole thing all at once kind of went. Still about 50 knots at 1 nautical mile. We're down low. Again, like I said, it's a little ambiguous. You take kind of an ensemble, 46 knots. And this is just about 15 minutes before it really went nuts as it approached Monette, Arkansas. 62 knot rotational velocity now at 1.5 nautical miles. And that's when you start really getting squirmy, when you get into the 50s and 60 pluses. Still, the depth of the mezzo, 12,000 feet. And I will typically use if I need a quantification, some of the stuff I did, worked on a few years ago. So I've got a VROT of 57 knots at 2 nautical miles here. And you can quantify that by taking the delta V, 115 knots, and dividing by the diameter. In this case, that would be 115 divided by 2.2, so right about 50, 55, 52. And then adding the depth of the mezzo, so in this case 3,600 feet, and it tops out about there. So about 12,000 feet, so 55 plus 12 is 67. And in values that start to exceed 50 and 60, we found back in 2019 that those are typically associated in supercells with storms that are EF2 or stronger in the next 10 or 15 minutes. In this case, we definitely got that as the storm approached Monette, Missouri, and really went nuts. In between this, over the course of this volume scan here, so we went up through the volume scan, and then it went back down. This is at 116, 117, 18, and then 117.55. You really start to see those low level rotational velocities pick up, and then here 76 knots. And again, we're getting de-aliasing algorithm errors, although in this case not enough to significantly discount. Like it's pretty good data. Then it really starts to go nuts, and then begins producing the long track EF4 that preceded the even longer track EF4 here at 84 knots. The tornado debris signature shows up there, and the storm blows through Monette, Missouri, where I believe there were fatalities that night. And it maintained that mezzo, and the mezzo actually stretched in this case, maybe even up to here at 28,000 feet. And that was a trend with this supercell that continued. The mezzo was tilted to the northeast for sure through the volume scan, but it maintained sort of this structural integrity that was really uncommon in my experience. Lots and lots of times you'll get new updrafts down here to the southeast. You'll get an occlusion shortly thereafter. This storm just sort of maintained steady state as one very nasty mezzo here. The low level rotation velocity is at least 75 knots down low, and even up high it maintains similar values. And then we got debris in this case up to 15,000 feet, and we have guidance that we put out to our forecasters using the low level rotation velocity that you've probably seen, which is based on the 0.5. 30 knots is, hey, we're getting into tornado warning territory if it's inside of 1 nautical mile, and it's also put into context of the environment. These are not hard and fast thresholds. And then when you get with debris, a debris signature, 40 knots tends to produce EF2 plus tornadoes at a higher rate, and then 50 knots tends to produce them even without a TDS, assuming you have a SIGTOR over 1. And you can kind of cheat those a little higher. You can go 55, 56 knots sometimes, a little bit higher. And if you're thinking maybe you've got evidence that you don't have a tornado or you don't want to go with those higher tags, but in this case, on this night, obviously they had this was not one of those nights. They had hit it as hard as they could. They went with the PDS tornado warning, and then eventually tornado emergency as it began to impact more populated areas, and we had more evidence, and it became clear just what kind of night this was going to be as that tornado tracked off eventually into Haytime, Carruthersville, Missouri, and then continued going into the region of western Kentucky there, where it produced even more impressive rotational velocity values. Now, when I'm looking at other supercells, it's still the same process. This is one in Central Texas on April 12th, 2022. So we go back. We got this storm. We got low-level convergence, really. We got inbounds, or outbounds and inbounds. The GRK radars over here. Go up to the volume scan. We got a mezzo there, and you've really got a pretty good mezzo here. that's a little broader. It's 44 knots at 3.2 nautical miles at 15,000 feet through about 6,000 feet AGL. Got a bounded weak echo region here at 14,000 feet, and that's topped out with echoes at 42,000 feet AGL over 50 dBz. And storm type divergence, you got inbounds and outbounds. And let's see, the 64 knots outbound, 91 knots inbound, so maybe 150 knots of storm type divergence, which is really impressive. Anything above 60 knots typically kind of signals a severe storm. And anything over 150 knots signals you got a pretty good storm. Here, another one of those weird situations where you had relatively low reflectivity in the tornado region, and then you had some suspect velocities that maybe were legit, but maybe were vertical side lobe contamination because you had such strong values here in this area of higher power return. Some of that may be getting translated to the surface, and it's really hard to tell. And you say, is that vertical side lobe? Is that good low level velocity data? I don't know. Well, the good news for most warning forecasters, and in this case we had a favorable tornado environment. We'd already had a tornado going on. This is, we'd already had a tornado, I believe, near Red Rock, or maybe this was just before the Red Rock tornado. I can't remember exactly how this day played out relative to this. I think this was just after. So we knew we had a very favorable tornado environment. You got a mid-level meso that is getting more impressive. It's tightening up. You got this spin here, and this is bang on in that region that you'd be worried about just south and around. So you've got sort of that tighter internal spin, and then you got the broader spin outside of it. And you've actually got an anticyclonic spin over here, which is kind of interesting, and you'll see that from time to time. Step forward, and you get that circulation. The good news with a deal like this is you say, well, that actually doesn't look like side lobe. That looks like a legit low-level circulation where you've gone from this sort of convergence signal to a more cyclonic convergence where you're getting these sweeping, conflicting commas. And then there is probably a tornado in progress. 43 knots at 0.14 nautical miles. That's definitely above that 30 nautical mile range. By this point, a tornado warning, I believe, had been in effect for some time, if I remember correctly. And then you start seeing that tornado vortex signature or tornado signature, 52 knots now down low. And you're not getting a ton of velocity de-aliasing. Well, you are, but you're getting it in a way that I feel confident that the radar is assessing it correctly, or the de-aliasing algorithm is assessing it correctly. And that continued on. Again, 54 knots. And then you've also got this broader signal here, which is actually a little bit stronger at 1.3. I went ahead and calculated the rotational velocity here because this looked like the tornado signature where this is the parent meso. But oftentimes I'll assess both just to have in my knowledge of what the meso aloft looks like, and this actually gets deeper and stronger. Now this, though, is what I'm talking about when I talk about a second meso forming. You get your inside circulation here that is really the parent meso. You look at, so there's your tornado circulation. You go up to the volume scan, and then now you start to see these enhanced velocities to the south at 20,000 feet. And those continue, and they've got continuity. They really get stronger. Step forward in time, and that persisted, even though it's a little bit low power return. Down low, you've got your tight tornado circulation, your tornadoes rolling, and people are starting to think, well, this town here is probably in a little bit of trouble. But what happened with this storm, you started to see this meso tilt with height, where back here, it's vertical, almost completely vertical, like the difference between where the tornado was down on the ground and what the meso looks like at 12,000 feet was only about 2 miles offset. And part of that is just that the storm is moving forward and the volume scans take 10 or 15 seconds, and part of it is due to shear. But this meso started to tilt to the north by quite a bit, where in this case now we're almost 3 miles out, tilted well north, and you're getting a new meso forming down here that's pretty robust through 20, 30,000 feet. And that was the sign of a new meso taking over, and then you had this storm in response to that become deviant and then go rearward and shoot north towards rural hill country there south of Kylene. And it caught some folks off guard, but if you're watching aloft, in the radar, a lot of times you can kind of say, oh, there's a new mesoform. Now, it's hard to say, oh, here in the next 2 minutes it's going to deviate. Because sometimes the meso continues and it doesn't deviate and it just keeps on keeping on. But a lot of the times, if you're on guard for deviation, once it starts to happen, it becomes easier to catch. And that's probably 101 with radar warning decision making and storm interrogation is once you're anticipating certain things to happen, you react more rapidly to them because you're not surprised by them and wondering what's going on. At this point, you notice even here, this low level CC, you had debris in this storm probably to 30,000 feet, which is pretty impressive. Anything above 8 to 10,000 feet becomes a little bit more suggestive of a strong tornado. That storm deviated, and then a little bit later, I think it reorganized. But there were lots of storm scale interactions here, lots of cells that were getting caught up, kind of getting shoved into the storm. And that kind of happened in north central Texas overnight on May the 4th, and I'll show that storm next. But here, that this big supercell ate this other little cell, and I think that helped some of the storm deviance. Where on this May the 4th storm, we had another little tornado supercell rocking and rolling near Lockett, Texas. And then it also deviated hard left, and this was really a weird storm. But you'll notice there was a little boundary right here and I think maybe it pulled on, and some of the forcing within that boundary maybe changed the internal storm dynamics. But with this storm, before it really went nuts near Lockett, I don't have my storm motion set. Let me do that real quick. There we go. So this storm had been producing 60, 70 knot rotational velocity. Just before it did that, you had the intense meso aloft showing up, where you had 50 to 60 knots at 3 nautical miles. It tightened up a little bit. The next volume scan down to about 2.2 nautical miles at 60 knots. And then here, even tighter, 70 knots at 1.2 nautical miles. And that's sort of screaming, hey, we're going to get a tornado. Of course, by this point, the tornado was probably developing. We got the debris signature about 6 minutes later, if I recall. Yeah, there's the tornado debris signature, although it's rural north central Texas, so pretty likely I would say that the tornado was already down. It just didn't have anything to damage. But what I noticed about this storm, more than I noticed a meso aloft, was that it slowed down. There was a new meso forming here to the southeast, which put me on guard for an occlusion. But the way this storm slowed down, it's cruising on a steady 210, 220, 230, 240 vector, and then it just stopped. And when it did this number, I'm like, I think the thing's about to hook. Now, I didn't understand at that time maybe how hard it was about to hook, because it still has a really good, consistent meso, but you'll notice that meso tilted to the north. At 28,000 feet, there's where it is, and then at 2,000 feet, it's 3.4 nautical miles south. So that meso started to tilt aloft before the meso occluded, and it really charted the path for the direction that storm took. Now, I don't have a lot of science and case studies to say this happens every time, but I have noticed it in the past where you'll see that tilt of the meso chart the path for the direction the tornado might be taking with some decent consistency. There's a new meso taken over there. Banded Weak Echo region's dislocated off to the east with the tornado kind of in the rear flank downdraft, and then the storm is occluding and beginning a path of being very deviant. This storm was weird because it maintained its intensity after it stopped. So it kind of stopped right here. And then it maintained its rotational velocity intensity for all the way up to here. That's 7 or 8 miles. And normally, those occlusions don't last that long. You saw the one we looked at before. It didn't last very long. It died off pretty quick. Once it got embedded in the storm, it died off. This one just kept on rolling. And I don't know if the storm coming up from behind it, the boundary, I don't know if maybe the meso decoupled from the Bernoulli processes or whatever that were causing the right moving storm motion Like this entire storm, if you eyeball it, it was cruising along, and then the hail core, even front flank downdraft, started taking a more northern approach, and then the storm reorganized over here. I don't know if it ever produced another tornado, but over the course of the next couple of hours, or next 30 minutes or so, storm reorganized well to the east, almost like a weak tropical cyclone. See the Boundary Wick Echo region off to the east now. So we have a tornado on the ground, or it had been on the ground here at Lockett, and we got a Boundary Wick Echo region near Ocala Union, 7, 8 miles, 9 miles east of there. So this thing did some weird stuff that I'm sure will be the topic of a paper or two in time. Now, when we're doing supercells, we're doing the full volume scan. We're looking at these Boundary Wick Echo region characteristics. We're looking at the reflectivity aloft. When we're looking at quasi-linear convective systems, we have a similar approach, but we're spending more time looking at the reflectivity signatures down low. I spend more time 0.5, 0.9, 0.8 than I do. Now, I'm still going to look at the whole volume scan because it can still give you clues. Like right here, we got 15, 16,000 feet, 60 dBz. So the updraft is stronger in this region than it is down here. But I'm looking at things like this notch in the line, this notch. Any disruptions, now that is a water tower or two or trees. I don't remember what that is. That's not a legit disruption. Cell mergers, things like this that I'm watching. And then we're really looking in the area where the line normal shear is the most perpendicular to the line and the strongest, exceeding 0 to 1 kilometer shear exceeding 15, 20 knots, 0 to 3 exceeding 30 knots. We can also get it in strong shear even if it's mostly perpendicular, like we did on April 27, 2011. But you can see here with that notch, we've got low level rotational velocity starting to show up around 40 knots at 2 or 3 nautical miles. And I don't remember or know exactly what degree of tornado developed out of this, but here you can see these little cell mergers and weird processes, and then it caught up to the line right here, little notch in the line, little notch in the line here. And if I remember, they were pretty aggressive in touring a lot of that stuff. Yeah, they had tours along that whole line. This was a phenomenal shear day, and there really isn't a good way to. There's this mid-level meso. The storms that are deep, rotating strongest and more deeply, still tend to produce the stronger tornadoes, but the relationship is just much weaker, and that's a big challenge that we have in the science right now, in my view. Is it's very difficult to go, okay, here's a line that's strongly sheared. Where are you going to get the strongest tornadoes? My gut would say meow and meow would be where I'd be most worried. But then sometimes it doesn't happen. Now, in this case, that little area I circled, we watch it here in Jackson, you see these little pooches. This did produce a tornado that went right through downtown Jackson. We had some data quality challenges, but the tornado went down through and did damage. And it's another thing that I've noticed very frequently here at 30, 40 miles from the radar. Actually, it's not quite that far, I don't guess. Let me see. Yeah, 30, 40 miles. You don't see all these little low-level circulations. So you get closer to the radar, you get down below 2,000 or 3,000 feet, and all of a sudden it looks like, oh my, we've had a bunch of new tornadoes. But I don't necessarily know that that's the case. There's a lot of times where I see them get closer and go, oh boy, has that line been doing this the entire time it's been traipsing across the CWA where there's little tornadoes? I mean, look at this. This is ridiculous. You're 2 miles apart and you've got separate circulations here within this line. And then you got another one up here, another one. And QLCS tornadoes are a real bear. And there's still not a real good way to go, okay, if I'm going to miss every tornado but the high-end EF1s, EF2s, how am I going to do that? How am I going to go about warning? There's not a real good way to do it yet. The stronger shear tends to produce the stronger tornadoes, but it's still nebulous as far as exactly how we can do it. There's some studies that have been put out about ZDR width and things like that, and I think those show some promise, the depth of the width of the updraft and things like that. But it's difficult to figure out how we're going to quantify that into operations and say, here's how you can attack it, here's what you can do, because I don't know, it's just difficult. It's a big problem. But you always look for the areas, you get here 11,000 foot, and you got to be cognizant of the fact that you're when you get up to tilt 4, your height, elevation with height increases dramatically due to the curvature of the Earth, and then the beam also gets much wider the further away from the radar you get. We're here at Jackson, over downtown Jackson, one range bend is 0.08 nautical miles wide. When I get out here to, around Yazoo, a beam is zero point 0.3 nautical miles, and then when I get way out here, I don't know what would be a good place to go. Around Cleveland, the beam is almost a mile wide. So you can think about what kind of meteorological features you can pick up here. Not only are you closer to the ground, but your beam angle, your range bends are much smaller. Right here, your range bends even are a mile wide. Not only, and you're also sampling at 9,000 feet elevation, so that's why it gets much harder to spot these features when you get at a range like that, which is in this case is about 90 nautical miles from the radar. It's not much that you can do. And our tornado intensity that we talk about really only applies inside of 65 to 70 nautical miles. You get beyond that, and you typically can't process the things that you can't see it. It's not going to resolve itself well enough. And I'll say too, with this 30, 40, 50, it's based off studies that Brian Smith and Rich Thompson did, and other folks worked with him on that. We did a couple of our own studies as well, and it's a statistical thing, so it doesn't always work perfectly. Sometimes you'll get really strong rotational velocities and relatively weak tornadoes for a variety of reasons. Sometimes you'll get relatively weak rotational velocities and you'll get relatively strong tornadoes. So it's one of those things where the meteorologist in the WFO has to constantly be assessing all of the different information that they know and the information that they don't know to make the best decisions for the public. So what you see here and what looks like the obvious thing to do isn't always the obvious thing to do, depending on what information that you're getting and what information that's available to them, what they can see on their situational awareness displays. It's very challenging. It's maybe fun isn't the right word. It's very interesting going through the process. And I guess it's fun if it's like a hailstorm and it's not hurting anybody, but like actually working on a deal like one of these, any of these tornadoes that I've talked about tonight are not very much fun to work. They're challenging and they're stressful. It's rewarding to get the warnings right and to be able to get everybody out of the way, of course, but it's not like going to the theme park, even though it is a bit of a roller coaster sometimes. So, well, that's a brief, well, it's not too brief. I went on for quite a while here, but that's a look into a piece of the process that goes into it. So maybe that'll be entertaining and interesting for some of y'all. I'll try to get this posted maybe to Twitter or Facebook or something like that here in the next day or so. Thanks for listening.